Right, I'm still working on this, as you would expect. I'm just doing some more tracing. I just thought I'd just try and look at a different section. Hold on a second, let's get the diagrams. So, what I was just doing is I was studying the block diagrams. I was just trying to find other approaches because I haven't been able to determine what it is yet. So I was trying to at least narrow other things down. Let's get some light here. So I've obviously identified that this 800 MHz VCO is going out of whack. I know that's wrong. Okay. And that's run off a 10 MHz reference, which I already fixed. That's that fault, which I already corrected. Phase detector is what's controlling the 800 MHz VCO and the 40 MHz VCO. So I thought I'll just check this path out, and that goes back round that way. I was looking through here to try and determine whether any of this could be playing up. So I've hooked onto test point 11, and what I'm just trying to assess is whether the subsynth gate array is playing up, in case that is feeding back into it, because it is all one big loop. In case that's feeding back in and causing problems from here, and then the 800 MHz is trying to compensate. That's where I was kind of just basically checking for to see if that's okay or not. Again, just trying to narrow down what it isn't rather than what it is. So here's the diagrams for it. This is the devices there as part of that is it clock generator and subsynth array, and the divide by 500. Yeah, divide by 500. This is what this is. Yeah, okay. This is the divide by 500 section. Well, that says 50 here. Interestingly. So anyway, that goes up here. Goes to checkpoint 11 or test point 11, which is where I'm hooked up to now. And it goes back into the low pass filters and feeds back into this quadrature detector and quadrature generator and so on. So I just want to check and see if the signal here is okay or not. So I've actually got two scopes hooked up. I've got that one there because it's good at showing glitches. It will show if something is glitching at all. And I've got the colors on and stuff on it, but I'll just have a look again. Actually, I think it doesn't help. I've got persistence on as well, so it stays on the screen longer if it does glitch. Which is one of the handy little features of the scope. And I've also got my Tektronix running. Let's get the light off that. The only reason I'm actually using the Tektronix at all is because it's got a output on the back, channel 2 output. So the channel 2 goes in here, is buffered and amplified again, and then goes back out the back, and then you can feed that into a counter. That's something I really wish the Siglent had. If the Siglent had that output on the back, then I wouldn't need the Tektronix at all. I could actually, put it away as a spare. Always like to have spare stuff. But yeah, so that's the only reason I've got the Tektronix running as well, because this has got a frequency display on it, but you can't trust it. It's actually not that accurate. One day I might actually pull this apart and upgrade it and make it a bit better. But so the Tektronix is running. I've just got it exaggerated on display. Turn the right way. I've got it exaggerated on display right now. I'm just trying to sort of look for anything which might show up. Well, I've got it hooked up to the top frequency counter. So that's what is at test point 11, and it should be 20 kilohertz. And you see how close that is. That's really, really good. That's the output of the generator right now. So I'm stepping down. If I zoom out a little bit, there you go. You can see that 20 kilohertz. Ignore that zeros. That's because it goes below the limit of that input. That input's got a what's it supposed to be? 100 megahertz input, and below that, so it's dropping off. But the all the way up, you can see that 20 kilohertz is stable, even when it's faulting on the output. So it's doing 20 kilohertz. If I was to skim through like that, you can see it's just sitting there stable all the time, absolutely fine. And if I look on the scope, I'll do the same thing. You might see a couple of little glitches when it goes through some ranges where it steps, but thinking generally it's pretty good. I mean, it's gone right down almost. There we go, see a little glitch there. Just there. Right at that point there. So between 250 and 240 it's doing that. And I know there is a range change just there. So I'm not too worried about that one. Main thing I was trying to look for is if it's glitching when it's faulted. And those frequencies where it shows that little glitch up there, that's actually outputting the correct frequencies, so that's alright. So it's basically eliminated. Let's look at it again. It's eliminated this section here as being faulty, and interestingly this bit here, because that is fed from this 40 MHz VCO. Right now I'm actually leaning towards this divider being incorrect. So this one I tried to do that visual measurement on, but yeah, this is the one I'm leaning towards right now as causing the problem, but I'm not sure. So I need to be sure before I can actually get much further really. But so anyway, I know that this piece here is okay, because the frequency is okay, the scope looks good, so I'm confident that bit's okay there. So this this section here I believe is okay. I've done some measurements here at this 40 MHz earlier on, because it's got a 20 MHz clock generator, and the fact it's out by 20 MHz was making me think, hey, is that a coincidence or not? Could there be a problem there? There still could be, but yes, just I need to do. I think I might do some more programming in this section just to rule this out completely. But I'm fairly confident it's okay. About the time I was only looking at frequency, I wasn't using the scope, so I might go back and actually revisit that with the scope and just make sure that what's coming out of here is okay. That's all part of what I was trying to track down. I mean, this is obviously a simplified overview. What I'm actually doing is look at the electronics diagrams and trying to do it from that. But so, and there's that gate array at U17, which I'm suspecting, just there. You see, it's all interrelated, and all the bands are wrong. So let's see, this band here is wrong. This band here is wrong. It doesn't actually mention the lower band. So I don't think it's just like anything in this section, because that all seems to be the same across all the bands. It's doing the same full right across that 20 MHz shift. It's not changing by much or anything. So actually there was a point I did see a 10 MHz offset. I did mention it earlier on. So maybe that is related. If it's halving, because there's a divide by 2 here. So it might have been that band I saw that 10 MHz difference. That's possible, isn't it? Certainly is possible. Anyway. So that's that VCO there. That's that VCO output. The main VCO. So yes, I was thinking about that 800 MHz VCO thing. And this is the actual 800 MHz VCO just here. So I can't measure 800 MHz directly on my scope, but it's got a divide by 4, which is right here. And there you go. Now this is actually a 100 MHz scope, but I can read 200 on it just fine, so that's quite good. My Tektronix does 300 anyway, but yeah, nice on this one. So that shows that 800 MHz is there. Now I've tried stepping through the actual frequencies where the error occurs, and that doesn't change at all. It's still rock solid. So that 800 MHz there isn't an issue. So at least that rules that bit out. Right, so I've just measured these test points here, 24 and 25, for this frequency here. So it's 40 MHz coming in. It's divided by 2. Follows flip-flop. Some buffering, and then it goes into this sub-synthesizer. I measured both of those, and they both measure 20 MHz, and they're both stable and don't play up at all when it's glitching. Or 14, whatever you want to call it. So here looks okay. So I don't think this sub-synthesizer is a problem. At least doesn't appear to be. Right, so let's measure in the synthesizer output. So obviously I've measured here. Now I'm going to measure the output of that U33. It's supposed to be between 10 and 19.9975 megahertz. I'm not quite sure what the distinguishing factor is between those, because all I'm actually getting out is 10 megahertz all the time, all the way through. So I'm not sure about that. I might have to do some reading. It might just be modulation related, but it doesn't seem to be band related. I've gone all the way through from 1 megahertz up to 441, and it stays at 10 megahertz all the way through. And seeing it's some kind of divider, unless it's looking for some minor steps. Let's see if I can try it actually. Let's do minor steps. Let's oh, there we go. Right, so I've just changed the step size. So okay, that's what it's doing there. That solves that question. So I've just changed it down to we're doing smaller steps anyway. This is put into a range I can just see it. 51 megahertz, stick it there. So yeah, if I do it in smaller steps, then it shifts there. You can see the frequency at the top there, hopefully, although it seems to be a bit glitchy. I don't know, I might have to look at that in a different way. Very ringy, but yeah, so at least that is actually changing that. This is 15, 10 there again. I've got a persistence on this, so it's probably not helping much. 10 again. So yeah, it seems that depending on what step I've got in front here, if I can get it on the camera. There you go. So that's what I'm stepping as those, so you can see it there. I've got that 1 second persistence on the scopes. Let's try another digit. Yeah, so that's what that's for. That's for doing the minor steps, not the big steps. That shows it quite well actually, doesn't it? See some shadowing on there. Anyway. Yeah, that must be what it's for. So something synthesizers doing the smaller steps. So I'm confident that that part is okay. So if I don't change it, only change the big steps, the frequency stays constant even when the unit is given the wrong frequency. So I'm 99.9% sure that this bit is alright. Okay. So eventually I'm going to eliminate everything and I'll be going, what the hell? Anyway, so we shall carry on. Okay, just had an idea. I remember I've seen that the frequency is often out by 20 megahertz, at least on the lower band. And I remember that I'd seen it being out by 10 megahertz. So I thought I'd just go through the frequencies again. Now I've got a bit more of an idea of what I should be looking for, knowing about the other flip-flop which has failed, which is causing unlock. So I can ignore that section of the issue. So I was trying to find out where the 10 megahertz error was coming from. So I was going through the bands and I thought, right, well, the 800 megahertz VCO here, that's just for a mixing signal. That's all it does, right? It's a fixed 800 megahertz. It turns off when it's not needed. So if I come in here a bit more, when you're on between 245 and 1 gig, well, 1.05 gig, it goes straight through, right? If you're on anything other than that, it comes through this mixer, and so anything up to 245 megahertz comes through this way. Alright, so I know that's okay. I know I'm getting the error here, which means it must be coming from this way. Right, the error is coming from this path. So this path comes from two sources. Right, the 245 to 512 and the 512 to 1050. I know that one there, that the upper one, is definitely giving an error, right? So I wanted to go through the 245 to 512, and that's what I've just done, right? And I found an error. So I'm currently on, there you go, 320 megahertz, 330 megahertz. That's out by 10. Right, so that's that 10 error. Now I've got it on 340, you can see it's glitching, which is probably that PO unlock. Then 360 is okay, 360 error again. Should be 370 there. So that's, yeah, see there's errors there. It's probably that PO unlock. Actually, I'll just confirm that. Let's get my spray. Let's give it a squirt. So I'm currently on 370. So it's likely to be that unlocked there, right? I get the thing to come out. Yeah, almost. Didn't get it very well. Right, there we go. So yeah, that's that faulty flip-flop there, right? 360, 350, yeah, 310, 320, 330, 340, 50 unlocking, 60 okay, 70. So, and there's that glitch there as well. So it's on that other band as well. I'm wondering if maybe just replacing that part is going to fix the whole bloody thing, you know. I'm starting to wonder that. I've been looking at this thing the whole way. We'll see. I mean, I've ordered the parts. I've ordered them from, I think, 3 different places. So, whichever one gets here first, will be the one I can put in there. But yes, that's interesting because the, yeah, so at least that's 10 megahertz out, which is half as much error. Which gives me a clue, which means it's being divided by 2 somewhere. That might help me. Anyway, okay, I'll look at the diagrams. So, just looking at this, that's the main VCR, which I know is wrong. Let's sort out the circuit I was probing before here. There's a VCR clamp and stuff like that. So that's where the VCR output is error. I know that every VCR is wrong. So here we go, divide by 2 right there. Okay, so that means the fault has to be before that VCO, as I'm suspecting anyway. So that just confirms what I've been suspecting. So I know that after this point's fine, after that point it's fine, because the only common thing is from that VCO and all this leading circuitry. So my colour shift keeps going off. It's on auto, it's on automatic and everything. Anyway, so you've got phase detector here, which I am suspicious of. Very suspicious. I think this low pass filter and stuff. Yeah, so that's the notch filters. I know the errors before there, and that's that other clamp which I actually disabled and stuff and played with, and open mod detector. Yeah, ignore those. So in here, I am very close. This is the other parts I've disabled, so I've ignored all this stuff. That can all be ignored. I've ruled that out. But by putting the ICs out, I did a video I did a few ago. Well, probably part of the same video I'm doing now. Earlier in the video. Phase detector is where it seems to come back to. Or this U17 gate array. Because this phase detector is detecting those 1 megahertz there and the 1 megahertz from here. So I'm trying to figure this out. This is derived from the reference, remember rightly. There we go, over here. I've got the high stability reference in here, so it comes straight through, that switches over. If it detects the signal, it switches automatically. I've already confirmed that correct. Comes through here, buffers and shit like that. All this is okay. I've already confirmed all that's right. It's one of the first things I've fixed on this thing. Divide by 10 to get 1 megahertz. I know that's okay, so that phase detector signal that side is perfect. Which narrows it down a lot, so it's either this phase detector or something in here. So just in this bit of the circuit is where that fault is. I'm leaning towards this part here, that U17, because if that's not dividing correctly, then it won't. It will tell the phase detector to well, it'll output the wrong frequency for the phase detector to compensate for. I'm actually wondering if what I need to do is actually try injecting another signal somehow. I might just look at this and see if there's actually a way of injecting a signal to disable parts of the circuit to eliminate it. That's what I'm looking at right now. And you saw me inject a voltage here before to manually control the VCO, and that will work fine. So was it just after there? Yeah, after that point it's right there. Test point 40. So I injected the voltage there, and that controlled the VCO fine. So I know that from there outwards is okay. So it has to be before this point, and there's not much there. So yeah, I'm concerned. But I'm going to have to look at this and see if I can find a way of injecting a signal in here. A stable enough signal which is precise enough to work. Yeah, that's what I'm going to have to try and figure out next. Oh, this is complicated stuff, but great fun. So I'm starting to probe around this end divider here just to try and determine what's happening in this section. As soon as I do suspect this is part of the problem. So I either want to prove it or otherwise. So I'm currently probing on pin 15 over here, which is there. Which is I think it's an output. It doesn't actually say very clearly, but I believe it's a data input into this flip-flop here. I think that's what it's doing there. Okay, so I think it is actually an output. This is mode L and C mod, I think it says, or O mod, I'm not quite sure. Anyway, I've got it hooked up to the scope. I'm currently on 100 kilohertz, and you're getting one little pulse. Right, so I have to adjust the trigger, and you probably see error and stuff. And if I go to 200 kilohertz, you get a bit more, 300, 400. Okay, let's keep on going up, and you'll see the pulses increase. And then I'm just going to scroll it through right now, just holding it down. Let's get a bit closer. See the pulse. So you start off by getting more pulses, and then they change value. The triggering is not right now, so let's just scroll it. Right, so that's what we're now getting. So and they gradually go up. So initially it increases the pulses, and once it's saturated with the number of pulses, because you look at the frequency there, it doesn't actually change. Yeah, come on, here. Right, so that's 1 megahertz there. See, that's maximum. So I'm just trying to determine whether things are working as they should be. Right, so what I'll do now, I've gone too far. Ooh, pushing buttons. Hold on a second. Let's get this right. Okay, so once it saturates, then it moves up scale. So that shifts up, goes up. That's what we're on now, 40 megahertz. So I'm doing 10 megahertz steps now, but then it steps down again, then up again, up, down, up, down. So these, based on the step sizes I've got, so that's 10, 20, 30, 40, so 50 goes back down the bottom again. That should be 60, 40, 50, 60 should be slightly higher, but it's going to 80. That's doing 90, that's doing 80 again. Right, so based on those values there, and the way that is the pulses are reacting, I believe that is doing the right thing, because it's all in line with what I should be doing for each step, which makes me a little bit more confident about this part. Now I've also got a probe 16, which is the input to this, I believe it is. Anyway, so I think it's TTO output from this device here, U20, which is actually fairly warm, it's quite warm. But that one there, let's change the scope probe around. So this is a very noisy output. I'm not quite sure if it's just my triggering is a bit dodgy or what, but it looks like it's got lots of jitter on there. So if I do this, let's see. So I'm on, let's start 10 megahertz, right? So 10 megahertz there. You can see the actual timing is changing each way. It's blurring each side. I've got persistence turned on, so it will do 1 second persistence. So the middle is looking right, but each end is off, which means the timing is changing. If I go to 20 megahertz, again same thing. 30 megahertz, same thing. 40, slightly better, but still the same. See, 50, now it gets really bad there, and that's when it's faulted. So what I think that is noise from the VCO coming through. That's the best one there, and that is on 80 megahertz and actually doing 80 megahertz. Whereas that's 80 megahertz, well 60 megahertz and actually doing 80 megahertz. So they should be the same in theory, right? If it is a control fault, it's not, is it? So that's the same frequency, 80 megahertz there, 80 megahertz there. The noisy one's the errored one. Which brings me back to here. And part of that circuit is this U18, here we go, U18, right? Which is this one here, which I know is faulty, that one there. So it could just be that all that noise and stuff is from this particular chip and that will go away. But the fact that noise is increasing when it's errored versus when it's given a correct one, that's a good sign. Because I've actually seen something which is different now. So it does make me wonder now if this particular chip, which I know has got a fault, is what's causing the entire fault. Maybe it's not just causing the 2 faults identified, maybe it's causing 3 faults, which is including that 20 megahertz offset. That's what I'm wondering now. So I've actually found something positive from that. So I might just have to just keep probing around and see what I can see. But I imagine if this, I think it's a clock input based on the labelling, CKNL and ICKL. So I'm guessing that's a clock input, which this then divides down in order to give the 1 megahertz output. But this makes me wonder, eh? 'Cause, I mean, that's showing, is that 21 megahertz coming in? Yeah, 21 megahertz. So it could just be some ringing in the circuit, but I'm not sure. It looks like a frequency error, jittering frequency. So if that's got to take 21 megahertz in, divide that down, 1 megahertz, that's divided by 21, isn't it? So I was actually thinking as well, if this chip has failed, and I can determine what frequency comes in, what frequency's got to come out, and that's the digital input there, I could probably write to an Arduino, maybe, depends on the frequency steps, stuff like that. I might be able to write a little microcontroller with the Arduino. Arduino's what I know, there's probably other stuff which is better for it, but to actually replace this chip, I could take that signal in, divide it down based on this data coming in here, and spit a signal out, you know, using PWM or something. But maybe PWM, maybe digital addition, you know, binary addition or something on the outputs. That's also possible. But anyway, I've got these inputs here which I haven't even looked at yet. I don't know what the hell they are. I haven't traced those yet. But I thought I'll just look at what I know. This is the 800 megahertz. Well, sorry, the high band VCO. So that's the, what's that? 0.49 gigahertz to 1.05 gigahertz from main VCO, right? Which I know is the one which is noisy and jittery when it's got that fault, and the and steps by that 20 megahertz amount. So I know this is coming in wrong. It's coming out wrong, but that is a loop, right? So it goes back out, it goes to the phase setter, which then controls the VCO. But if there's a fault in here, it could cause this to possibly divide incorrectly, so it outputs the wrong frequency, which then makes that wrong, and so on. So, you know, but that is pulses coming out of there, and you can see it's actually got a bit of ringing in there and stuff. But I probably don't have the ideal setup for this. But yes, this is making me wonder about that chip there. Eh? You know, it might not just be that. This U20 is also quite hot, so there's a bit of warmth in that. I might actually look to see if I can find a replacement for that. But what does it say? MC12013. Yeah, never heard of it. So I don't like my chances of getting a replacement. And unfortunately, it's not in a socket unlike a lot of the other ones. Probably because it's got a higher frequency going to it, so they don't want to reduce the ringing and stuff going to it. But which means I have to cut it off the board and replace it with another one. And it might be pointless anyway. Yeah, so I've actually found something at least, something which correlates with the error I'm seeing, which is great because it means it's not. I know the error is showing up here. Whether that's just coming in from here, that's the next thing I should look at. I should look at that actually, see if I can figure that out. We'll see, but it's definitely, you know, that's pin at 16. That's 16 noise. That's, you know, something at least, you know. But then I think it tracks back to this IC over here. Right, that'll do for now. Right, so now those parts have arrived, I can actually put them in. I'm only going to do one thing at a time. I've got various parts in case I needed them because I wasn't sure about them. So we've got the main one, which I know is this one here, the MC10131, which I know is fried because it doesn't react right. Shouldn't be able to spray it a little bit of freeze spray and have it completely change profile on how it works. So this can come out. Now I'm going to try the AliExpress version first, because out of all the ones I've purchased, these are the ones which are most likely to give problem. So I'd rather rule those out. But they look like old stock, so I think they're okay. They're dated 85, and the Futurelink ones are dated, was it 81 was it? Oh, yeah, 81. So, I'll close these pins up. So I'll pop that in there, then I'll plug in the power. And I'll chuck the scope on there. Yeah, they've got some slight corrosion on the top of those pins, so yeah, it's definitely old stock, not a copy. Let's hook this up. Power things up and see if it actually works. Let's see what's backing up. Let's see what I can see from here. Probably not enough. Well, it's currently sitting 80 megahertz. What I want to look at is the noise on that pin, on that test point I found before. Was it 16 wasn't it? Just there. That was very noisy before certain points. And 80 as well. Over that. That's working. That looks like it solved that. Oh, am I speaking too soon or not? Oh no. Yeah. Okay, so changing that chip has solved the other issue I had as well, which is why I stopped working on it. I did a couple of videos troubleshooting trying to find the 20 megahertz offset which I had. Trying to trace that down. And the closest I found was noise on this pin 16. This is yeah, it's test point 16 just here. I had lots of noise there. which is fed partially by this IC I just changed here, the NC10131. So it's fed from that, in that area. It's all like linked together, part of the face to feed and everything. And I was starting to suspect that maybe that chip was playing a part in a 20 megahertz offset. This is a perfect 20 megahertz, which it may be one if it's a digital control anyway. So I stopped working on it, thinking that maybe it is this chip as well, not just that jittering I was getting. The other test I've got to do is change Fluke's counter inputs. Let's chop this down. So 10 megahertz. So the other test I've got to do is go right down to trying to get the camera work with it. Right down to as low as it will go. So because the bottom end is playing up. Right now it's all working fine. Yep, down to 10 kilohertz. That's it. It's working. Cool. It's actually behaving the way it's supposed to, which is brilliant. It's going to scan up through the frequencies all the way up to the top, 1 megahertz at a time. Interesting. There's a little bit just there, which wasn't there just now. There we go, 90, 91, there we go. That's not working then. Issues. Okay, so there's still some problem here. So 176. I can get both in this picture at the same time actually. No, I can't off from here. So, alright, 177, 178, so it's jittering around. So there's still an issue there, but it's narrowed it right down. So, that one's about 176, that's when I find out the limit. Something else weird, I didn't see 160s before. Yeah, around there, here we go. 198, 199 is not right either. That's out, now it's doing 151. But the scope's looking okay. So there is another fault somewhere, which really doesn't surprise me. Oh, I know what it could be. Yeah. Silly me, I might be fine. I'm at the top end of my Fluke's counter on that range, so it's back to 170. This one's only rated up to 120 megahertz on the input there, so it could be that frequency's topping out. Let's do that. This makes much more sense. Here we go, that's fine. That's okay. Oh, there's something just there. 242, 243, 244, 245, 246. I'm sure I saw something there just now. Just been counting rounding or something. Let's go through those ones again. Because it's rounding down slightly, so it makes it a little bit hard. It flicks down to 9s. So it might be okay. Could have been the way it just appeared. Right. Well, it's looking pretty good so far. It could take a little while though. When it gets to about 512, might be just a rounding going on. Hold on. When it gets to about 512, I think there's another step. Yeah, that's right. Just that fancy rounding. The 512 is another step, and it might be a problem there. 11, 12, 13. Cool, that's looking alright. So now I might go up in 10 MHz steps on it. That's a bit harder to keep an eye on. That's it. The whole frequency range works. It looks like I might have solved it. There we go. Right. So that's the culprit right there. So this one I see here was responsible for 3 faults. The bottom end not working below, I think it was below 20 megahertz, I think it was, it played up, and the very bottom, I think it's about 10 kilohertz to 40 kilohertz not working, and the 20 megahertz / 10 megahertz offset on certain channels. So that's the fault to watch out for. If you get that, then this chip is something worth looking at. Right, so I'm going to stop this video now. We'll do some further testing. Now it seems to basically be working, and see if there's any other faults which I can find. Right, so I've got my spectrum analyzer running. I've got it hooked up to that. I've got a 0 dBm signal coming out of the Fluke. So it's going to go right down to the bottom. I've got a span starting at, start frequency of 1 megahertz, finishing 1100 megahertz. So you should be able to see it sweep right through around that line at the top. And I'll do a similar thing for different output levels just to prove they're okay. So, right, starting now. I'm going by 10 megahertz at a time. There's a couple of glitches where you'll see it changes ranges on the Fluke, so you see a glitch. All the way through. Sweet. No funny jumping around with me. So let's just change the amplitude. Let's go to dB. Let's go down. Let's see, let's do, as you can see each step is going right, so that's 0 dB minus 10, yeah, minus 20, minus 30, minus 40, minus 50, minus 60, minus 70 disappears. So I'm going to do a quite low level, that's minus 50 dBm, show the lighting's catching it. Go back to frequency again. And I'll go back down the range again in turns. If you just to test the attenuator stuff out. See, there's a little bit of variation there, but again, because of the span, it's not going to be scanning perfectly. See, a little glitch just there. That's the changeover at 245 megahertz. You can see there. So There's nothing. So yeah, all the way through. Sweet. So that's actually looking pretty good. The only thing I've got to do now is modulation tests. That's the only thing that comes to mind, at least. And go from here. Oh, so I've got this spun around so you can see it. I'm just sitting on 80 megahertz. This is what I'm going to leave it on. I've got minus 10 dBm output. I've got this plugged straight into my Boonton modulation meter. I've got it set to 30% mod AM 1 kilohertz. And that's what it's giving. I'll switch it to 400 hertz instead. That's still the same. Doesn't change, which is good. I prefer 1 kilohertz test times myself, but let's see. What do we want? AM modulation. Let's change this level. So I might go all the way up from 99. So that's 99. I'll go 90, 80, 70, 60, 50, 40, 30, 20, 10. Right, so it's not too far off. I mean, I don't know which unit is out of calibration, whether it's my Boonton, which is a bit out, whether it's the Fluke, which is out. Obviously there's a bit of an error there, but it's not a huge error. I think the worst is 50%, it's out by about 10%. Everything else is slightly better than that. So yeah, it's not too bad. So I'll do FM modulation, turn AM off. This is a good question. Starting percentages. Percentage of what? FM. Oh, that's interesting. I hadn't considered that. That's interesting. Well, let's do 5 kilohertz. Thought that would work, but it doesn't. I should figure out how to use this, but that'd be fun, wouldn't it? I thought that would work. Oh, here we go. I'll push the right button. That button there. FM. Right. It's very dim, but you can see it there. Kilohertz deviation just there. I might actually see if I can increase the voltage going to this display, make it slightly brighter. So it's set on 5 kilohertz, and that's what I'm getting. Let's step this over. Let's go up by kilohertz at a time, eh? 10. Okay. 15. 20. 25. 30. It's bang on there. 40. Also bang on. Let's go up by 10s. 50. 60. 70. 80. 90 kilohertz. Yeah, it's pretty close. So what I'll do is I'll just go 2.5, let's do that, eh? 2.5 kilohertz. Get the light off it and get a sit. 2.7, let's do 10 divided. So it's pretty close. So the modulation appears to be okay. Let's go 400 hertz. Yeah, it's still fine. So it works. You actually do AM, FM at the same time, which is really interesting. I've never seen that before. He doesn't seem to like that. Why? So, yes. So I do AM only. I'd be confused by that because I'm on that one still. Yeah. Interesting, so you can do AM and FM at the same time, and the Boonton handles it. So that's the other thing I was going to show you. This test point here, I originally used it on this scope here, and you can see the frequency jitter. There's a bit there, like phase noise or something in there. Interesting. So So yeah, it's still there, but yeah, it's not jumping all over the place now. It's consistent at least. So it must just be the way that actually works, because I can't fault that. I can't find out where that phase noise coming, but it is actually reduced quite a lot since I changed the IC. So at least. So frequency range is working, modulation is working, levels are working. I haven't tried doing any saving and recording memories. I don't know how to do that yet. Let's have a look. Let's just try this. 26.5 megahertz. It's a nice channel. Store that. Where? I don't know how to use this. Don't know. I have to figure that bit out. But anyway, the rest of it seems to work. I have to see how the memory stuff works. So it looks like I've actually fixed it. What I'm going to do on here, it's got the RF output, which is obviously on the back with the modulation input, which is one of the options for this, which is set by this switch just here. Number 4. That was actually turned off. It's supposed to be on when it's got the rear output, so someone's obviously messed with it. It's also got the the black pen on it. So someone's obviously marked that for some reason, obviously when they're playing with it. So I'll turn it back on. All it does is compensates a little bit for the RF level drop on here. But in saying that, when I was looking at my spectrum analyzer, it's actually, I've got 0 dBm output on it at the time, and I was getting around 1 dB in some cases. So it might be it doesn't actually need that compensation turned on in this case. Anyway, what I'm going to do, I'm going to open up this port on the front. I've ordered some sockets. I'm going to keep the original all intact because it's got this hard coax on most of the back. It runs down there. From the front, it comes out at this point, just here. So what I'm going to do, you can see where the socket goes just down there. I've ordered some SMA cable and a jack to go in there. I'm just going to unplug this, put the jack on, and run a little SMA cable between the two. And it's only going to be a few inches long, so I'm not too worried about any losses or anything like that from it, or shielding problems. I'm just going to do that because obviously I'd like to get the hard coax one, but came with it, but chance of getting that's almost impossible. So that should do the job anyway. And then I'll give me the output on the front, which I prefer. I might move the modulation input as well to the front as well. That would make sense, but that's going to be pretty simple. It's just a BNC, so no problem there.